Perspective, Class 9, Video 1. In this video we're going to talk about central projection. We've already spoken about parallel projection in previous videos. If you recall, parallel projection is a very simple method of projecting 3 dimensions down to 2 dimensions, and it has a lot of benefits and a lot of applications. For example, it's used in technical drawing, like product design, architectural drawings, it's used in some art, and it's used in isometric video game graphics. But parallel projection has some downsides as well. Perhaps the most striking downside is parallel projection does not produce images which are realistic. And by that I mean the images produced by parallel projection are not what you would see with your own eyes. What you would see with your own eyes is different to what a parallel projection would give you. And this is where central projection comes in. Central projection is what you would see with your own eyes. An image created using central projection should be the same as what a human would see with their own eyes. Well, there's a slight caveat to that in that humans have 2 eyes, which causes a negligible sort of technicality. But I can confidently say central projection is what a cyclops would see with their own eye. Let's just go straight to the definition. So central projection depicts each point on the viewing plane at the exact spot where the line of sight, so the line of sight is just the ray from the eye to the object, hits the viewing plane. And by default, we always consider the eye to be at the origin. Okay, so the idea is there's an eye, there's a viewing plane, and there's a point in the distance. You draw a line from your eye to the point, and wherever that line hits the viewing plane, that's where that point gets depicted. So let's do a geometric example. Okay, so here's a coordinate axis, and I've drawn x equals d. One thing I want to say is this is 3 dimensions. It just looks like 2D, but what I've done is I've rotated it so that the y-axis is going into the page. So the y-axis is going straight into the page. Okay, so it's 3 dimensions, but to simplify the drawing, because it's hard to draw in 3 dimensions, so to simplify the picture, I've made it so the y-axis is going straight into the page, so you can't see it, but it is actually there. And now let's just draw a point somewhere. How about right here? And I'll label this point X, Y, Z. And all you do now is you draw a line from the origin, which is the eye, to your point, like that. And wherever that line hits the viewing plane, which is right here, this is where XYZ gets mapped. So I don't know what this point is, so I'll call it X prime, Y prime, Z prime. So under central projection onto the plane X equals D, we have that X, Y, Z gets mapped to X prime, Y prime, Z prime. This is the geometric interpretation of what's going on. Okay, your eye is at the origin, X equals D, this is a plane. This is the viewing plane. It looks like a line, but it's not actually a line because you can't see the y dimension. The y dimension is going into the page. It's actually a plane. Okay, so x equals d is the viewing plane, and I take my point, I draw the line between my eye and the point, and then wherever that line hits the viewing plane, that's where I depict my point. And this is a very natural way of projecting things. Okay, this is based on real life, what happens with your eyes. I mean, your eyes are photon receptors, right? Where the photon hits your eye, it produces a little burst of information which goes to your brain. So you think about this plane, this viewing plane, as your retina, and this line is the path the light photon takes, and then the light photon hits your eye, hits your retina, and that sends a message to your brain. Okay, so this is the geometric interpretation of central projection. Now it's sort of our task to work out a formula, right? because I don't know what these coordinates are. It would be ideal if I could have a formula which told me what is x prime, y prime, and z prime in terms of x, y, and z. I want a formula for central projection. So let's think about what I know. Okay. Well, I see two facts. I see fact number one is x prime, y prime, and z prime lies on the plane x equals d. Okay, it's on the plane x equals d. And fact number two is x prime, y prime, and z prime lies on the ray generated by x, y, and z. Or another way of saying this, well, okay, I'll just say that. So x prime, y prime, z prime lies on the ray generated by x, y, and z. Okay? And now, what can we deduce? Well, from fact number one, we know that x prime, y prime, z prime has to be equal to d y prime, z prime. Or another way of saying this is we know that the x prime has to be equal to d, because the x coordinate has to be d. It lies on the x equals d plane. Okay, and from fact number two, we know that x prime, y prime, z prime, it lies on the ray generated by x, y, z. So that means it equals lambda x, y, z for some lambda. For some lambda bigger than 0. Okay? Bigger than or equal to 0. Thus, this means that if we put these two things together, we have that d y prime z prime is equal to lambda x, lambda y, lambda z. Okay, so this means, in particular, d is equal to lambda x, and thus lambda is equal to x over d. Okay, and this is important. This is like we're pretty much done now. Because lambda is equal to x over d, and we know that x prime, y prime, z prime is equal to lambda xyz, this is equal to, oh sorry, my fractions are the wrong way around. It's not x over d, obviously, it's d over x. d over x. So this is equal to d over x, x, y, z, which is equal to, if I multiply this through, I could leave the d outside and multiply by the 1 over x to get 1 y over x, z over x. Or if you want, you could include the d, and you could write d dy over x, dz over x. Okay? And this is the formula. This is what we were after. Okay? Because now we know that central projection onto the plane x equals d sends the point x, y, z to d times 1 y over x, z over x. This is the formula that we were looking for. Okay, and you don't need to memorize this derivation off by heart. I just thought it might be useful to help you remember the final formula. Okay, but it is important that you know this formula here, and we can do this same calculation for different planes. So instead of projecting onto the x equals d plane, we could project onto the y equals d plane, or the z equals d plane. And if you do a similar calculation, you get this theorem right here. And this theorem tells you that central projection with I at the origin is given by the following. So if you're doing it onto the x equals d plane, which we just did above, we worked out that this is the formula right here. Okay? But you can do the same calculation for y equals d and for z equals d. If you do y equals d, you get this formula here. And if you do z equals d, you get this formula here. And notice there's a pattern going on. I mean, like, you need to remember this however is best for you. But, I mean, the way I remember is you always times by d. And if you're doing it onto an x plane, you divide all the coordinates by x. If you're doing it onto the y plane, you divide all the coordinates by y. Right? Because, obviously, 1 is the same as x divided by x. Right? This is the same thing. It's just you write this as 1 instead. So if you're centrally projecting onto a plane z equals d, times everything by d and divide everything by z. And that's the formula. So like I say, it's very important that you memorize all of these formulas. That's the end of this theorem, and that's the end of this video.